In this example, we're going to calculate the outlet pressure of a packed bed. And the idea is that because it's packed with, for example, a catalyst, there's going to be a significant pressure drop through the reactor. We're given information on the size of the catalyst particles, diameter of the tube, its length, and information on the gas feed rate and molecular weight, viscosity, and the feed pressure. We want to know the outlet pressure. To determine that, we're going to use the Ergun equation. I've written the Ergun equation here. There's another screencast that describes each of the terms, but briefly, this is the diameter of the particles. This is the void fraction, cross-sectional area, the viscosity of the gas, mass density, volumetric flow rate, and then distance down the reactor and pressure in the reactor. Now, to be consistent, we're going to use units where kilograms, meters, seconds, and pascals are the units that will give us in this equation the consistent values, because kilograms per meter per second squared is pascals. And we're also going to need to calculate the volumetric flow rate assuming ideal gas. So that's the total molar flow rate times gas constant, absolute temperature, divided by pressure. And of course the volumetric flow rate in this case is increasing as we move down the bed because the pressure is decreasing. So first we're going to look at some of the numbers that we'll need to put into the equation. The area of the tube, pi times the diameter of the tube squared over 4. We look up the gas constant, 8.314 meter cubed, pascals, moles, and Kelvin. Rho V is going to be rho 0 V0. This is just the mass flow rate, and this is a constant for our system, and it's given 50 kilograms per hour, and we have to convert to seconds. And then we have the molar flow rate at the inlet, and since there's no reaction, then the molar flow rate is a constant, and so we're going to determine that from the mass flow rate and the molecular weight. So now we're ready to substitute into the Ergun equation. So I've written down the Ergun equation where I've substituted for the volumetric flow rate in terms of gas constant, temperature, molar flow rate, and pressure. And I'm going to bring the pressure to the other side of the equation because I'll end up separating variables and integrating this equation. So I made the substitution where the volumetric flow rate term I've written here on the next line. And we want to check to make sure units are consistent. Should be Pascal squared over meters. Indeed, if we look at the right side, we're going to have Pascal squared per meter because we have kilograms per meter second squared, and we have 1 over meter. So if you follow through and look at all the terms, you'll see that this is consistent. A Pascal, kilogram per meter per second squared. And so here's the intermediate numbers. Mainly point out this is the laminar flow contribution. And then this second term, the turbulent one, is certainly the dominant term here. Because of this large number, I'm going to convert 10 to the 5th pascals, 1 bar. So now we have an equation that relates the pressure change as a function of distance. We can integrate. Inlet pressure 12 bar. The outlet pressure is what we're solving for. Inlet distance is 0. The outlet distance is 30 meters. So if I make the substitution, p squared over 2 with these limits, and this is just times 30. So if we do this calculation, take the square root, pressure 8.8 bar. So the pressure drops through this bed from 12 bar at the inlet to 8.8 bar at the outlet.